Okay, so the next operator is called the implication operator. So given two propositions, P and Q. So P, the compound proposition. Proposition P implies Q, denoted by P implies Q is the proposition which is true, if P and Q are both true, or if P is false. Okay, so the truth table looks like this. You know, P, we have P, Q, P implies Q. Okay, so if P is true and Q is true, if both are true, by definition, P implies Q is also true. If P is true and Q is false, so I cannot conclude something false from something true. So this would be false. But if P is false, then P implies Q will be true, regardless of whether Q is also true or Q is false. So in other words, from a false statement, I can conclude a true statement, a true or a false statement. So the overall, the compound statement will be still true. Okay, so here, note, when we say P implies Q, so P, so in P implies Q, P is called the hypothesis, and Q is called the conclusion. Okay, so let's look at an example. Let's say, for example, if I say if, so this is, well, here I said P implies Q, but sometimes this is called if P then Q. So these are also other common, terminology. So let's before the example. So let me say remark. So P implies Q is commonly read as if P then Q. Okay, so when we say if a statement, then another statement. So the statement coming after if is called hypothesis or assumption, and the statement coming after then is called conclusion. So P is called hypothesis, or assumption is also called. Q is called conclusion. Let's write hypothesis or assumption. Q is called the conclusion. All right, so let's look at an example. Let's say if 2 plus 2 equals 5, then 2 times 3 equals 7. So is this true or false? Well, see, this part is called, we call P, which is the assumption. And is that true or false? 2 plus 2 equals 5 is false. And this one is called conclusion. And I denote it with Q, and this one is also false. Right? And false implies false. So let's look at the table. If P is false and Q is false, P implies Q is true. Right? So P implies Q is always true, except in the case where P is true, Q is false. Only in that case, P implies Q will be false. In all other cases, P implies Q will be true. So so this whole statement is true. False implies false is true. Okay, so let's look at another example. Let's say if today is Monday, then I will go to the mall. So this statement will be true. Will be true if, so in which cases can I say that this sentence is true? So if today is not Monday, I can still say that this statement is true because, you know, the assumption does not hold, right? So the whole statement can be still considered as true. So this will be true if today is not Monday, or if today is Monday and I go to the mall, right? So this is what we said here. P implies Q is true. If P is false, see, look at the third and fourth case. If P is false, P implies Q is true. And also if P and Q both are true, again, P implies Q is true. So therefore here we said if today is not Monday, P is today's Monday, today being Monday. So if today is not Monday, P will be false, the whole statement will be true. Also, if P and Q both are true, meaning that if today is Monday and I go to the mall, so the whole compound statement is still true. So only in one case, this will be false. In what case this will be false? Is true, will be true if this and the compound statement above is false if today is Monday, so if P is true, and I do not go to the mall. If it's Monday, but I don't go to the mall, then this statement is false, because in the statement, it says that if it's Monday, then I go to the mall. So let's assume it is Monday and I don't go to the mall. So in that case, this statement will be false. But if it's not Monday today, the statement will be true. Or if it's Monday and I go to the mall, still the statement will be true. Okay, so one more remark here is that note a compound statement of the form P implies Q is called a conditional statement. It's called a conditional statement because there is a condition or assumption or hypothesis P and a conclusion Q. Okay, now whenever we have a conditional or a conditional statement, we can talk about few things such as converse of a statement, inverse of a statement, and also contrapositive of a statement. So let's look at the definition of each of those. So converse, inverse, and contrapositive of a conditional statement. So consider P implies Q. Okay, so then the converse of P implies Q is defined as Q implies P. The inverse, so this is the first definition. Second definition, the inverse of P implies Q is defined as negation P implies negation Q. And the third one, the contrapositive of P implies Q is defined as negation Q implies negation P. Okay, so I'll give examples for each case. But the important thing to know is that, so in my experience, always there is, students get confused about a statement and converse of a statement. So if a conditional statement is true, the converse of that statement does not have to be true. Okay, so this is very important remark. So let's look at an example. Let's say the converse of if it is Monday, then I will go to the mall is if I go to the mall, then it must be Monday. See? Let's look at the definition again. The converse of P implies Q is defined as Q implies P. So here when I say if it's Monday, then I go to mall. So P is being Monday, Q is going to mall. Now, converse is Q implies P. So it will be, if I go to mall, then it must be Monday. So let's assume the first statement is true. If it's Monday, then I go to mall. So I have a schedule that, always on Mondays, I go to mall. Let's assume this is true. Can I say that the second statement is also true? Just imagine, I have a schedule that in my schedule, well, mall could include grocery stores as well. Let's say Mondays, I have more time, free time, and therefore on Mondays, I always go to mall, including grocery stores. So if it's Monday, then I go to mall. So let's assume this is true. On Mondays, I go to mall. Can I say that the converse is true? If I go to the mall, can I say that it has to be Monday? No, because I didn't say anything about the rest of my schedule, right? Let's say, for example, my schedule could be in a way that on Mondays and Thursdays, for example, let's say I don't have any class to teach, and therefore, let's say I go to the mall. So yes, it's true that on Mondays I'll go to the mall, but also on Thursdays I also go to the mall. Therefore, I cannot say that if I go to the mall, then it has to be Monday. That will not be true. In the situation where I go to the mall on Mondays and Thursdays, the second sentence will not be true, although the first statement is true. So my point is, if a statement is true, a conditional statement is true, then the converse of that statement does not have to be true anymore. It may be true, but it may not be true. Okay, so note that assuming, so let's call this one statement 1. Statement 1, and let's call this one statement 2. So assuming that statement 1, the statement 1 is true, we cannot conclude that the statement 2 is also true. Because, I may go to the mall on Mondays and let's say Thursdays. So I'm saying that we cannot conclude that the statement 2 is true, because it's possible that, let's say, on Thursdays I also go to the mall. But I'm not saying that it cannot be true. It may be true, may not be true. So in the situation where let's say I only have enough free time to go to the mall on Mondays only, in that case, the converse will be true. But in the situation where I have free time on Mondays and Thursdays, in that case, the converse will not be true. So if a statement is true, the converse may or may not be true. Depends on the example, depends on the case. Okay, so or another example, let's say a mathematical example, let's say if x is equal to 2, then x squared equals 4. So this one is true, right? If x is 2, then x squared is 4. What about the converse? The converse of this statement is if x squared equals 4, then x is equal to 2. Is this also true? If x squared is 4, then x could be 2 or minus 2, plus or minus 2, right? So if x squared is 4, I can conclude that x is equal to plus or minus 2, but I cannot conclude x is equal to 2. So this is false. The converse of this statement is this, which is false. Which is false, again, because if x squared is 4, then x could be 2 or x could be minus 2. Okay, so the truth table for Q implies P How does the truth table look like? So see P, Q, and comparing with P implies Q. So this is P, Q, P implies Q. And then we also have Q implies P. I want to draw a truth table that has both one column for P implies Q, one column for Q implies P. So the examples that we have seen so far indicate that P implies Q and Q implies P are not equivalent with each other, meaning that in a certain scenario or certain situation, one of them could be true, but the other one could be false. Right? So in this sense, they are not equivalent with each other. Now I want to verify this with the table. So now let's look at this table. Now for the table, we said, we have to include all the possibilities. So let's say if P is true and Q is also true, or P is true, Q is false, or P is false, Q is true. And if both of them are false, okay, so if both of them are true, this will be true. If P is true, Q is false, then true implies false. We said it's false, if you remember. But Q implies P will be false implies true, which is true. False implies true, this will be true, but false implies, false implies true is true. For the other one, Q implies P will be true implies false, which is false. And if both of them true, false, then the P implies Q and Q implies P will be both true. So when we look at these two columns, so these two are not the same. So not the same column. The first row is same, the last row is also same, but the second and third rows are different. So in this sense, we say that P implies Q and Q implies P are not equivalent, are not logically equivalent with each other. So let me define the logical equivalence of two compound statements. logical equivalency so two statements, two compound statements let's say f of p and q and g of p and q are called logically equivalent if the resulting truth value of f of p and q and g of p and q are the same for each case of truth values of p and q. In other words, the columns of f of p and q and g of p and q are exactly the same in the truth table. And the notation is f of p and q equivalent with g of p and q. So I hope that this notation of f of p and q is not confusing. I just say f of p and q because, it could be any compound proposition. So it could be P implies Q, it could be P or Q, it could be P and Q, it could be negation P and Q. So because I want to provide a general definition, I just called it F of P and Q. It could be anything, P implies Q, P or Q. G of P and Q, again, could be anything, P implies Q, Q implies P. So any two compound statement proposition that I have, if the resulting truth value for the first compound proposition and the second compound proposition is exactly the same for each possibility of truth values of P and Q, then in that case, we say they are logically equivalent. The easier way to describe this is with truth table, like I said here. Look at the column of if you want to know two compound propositions are equivalent or not equivalent, look at the column in truth table for those two compound propositions. If the columns are exactly the same for each row, then they are equivalent. If they are not the same, even at one row, then they are not equivalent. So in this case, again, like I said, the first and fourth row are the same, but the second and third row are not the same. For the compound proposition P implies Q and compound proposition Q implies P. Therefore, these two are not logically equivalent. So in the case of converse of a statement, we can say that Q implies P is not equivalent with P implies Q. Okay, so since the columns of P implies Q and Q implies P in truth table above are not exactly the same. All right, now let's look at inverse. In the case of inverse of P implies Q, we already provided the definition. Let's look at the definition one more time. Here, inverse of P implies Q is defined as negation P implies negation Q. So let's look at this example again. If it's Monday, then I go to the mall. So let me write it as an example for inverse of P implies Q. So the inverse of, if it's Monday, then I go to the mall. The mall is, if it's not Monday, right? Let's recall ourselves. Inverse of P implies Q is negation P implies negation Q. So negation of if it's Monday is it's not Monday. So if it's not Monday, then I will not go to the mall. Go to the mall. So again, is this equivalent? So I have two statements here. If it's Monday, then I'll go to the mall. If it's not Monday, I'll not go to the mall. Are they equivalent with each other? In other words, if the first statement is true, can I say for sure that the second statement is also true? To think about different possibilities. Let's say I know as a fact that if it's Monday, then I go to the mall. But can I really conclude? Can I be sure? Can I have a guarantee that if it's not Monday, then I will not go to the mall? Of course not, because like I said, I may have free time on Monday, therefore I'll go to the mall, but maybe on other days I also have free time. Let's say, for example, on Thursday, again, I don't have a class, therefore on Thursday I also go to the mall. So again here, if the first statement is true, then the second statement may or may not be true. In other words, these are again not logically equivalent. Let's verify it again with a truth table. So truth table. So P, I have P here and Q here, and then P implies Q here. Okay, I also need negation P and negation Q. So let me include negation P, negation Q, P implies Q, negation P implies negation Q. So again, the possibilities are the same four possibilities that we had in the previous cases. So both of them could be true, or true and false, or false and true, or false and false. So these are the possibilities. Now, if P and Q are both true, well, let's look at negation P and negation Q. If P is true, negation P will be false. If Q is true, negation Q will be false. So negation is just the opposite of the original one. If P is true, negation P will be false. Q is false, negation P will be true. And if P is true, negation P, if P is false, negation P will be true. Negation Q is true, negation Q is false. And the last possibility, both of them are false. So negation, therefore, will be, both negations would be true. And for P implies Q, again, how do I know P implies Q is true or no? Again, according to the definition of this operator, P implies Q is always true. There's only one exception, which is false. If P is true and Q is false, true implies false will be false. All other possibilities will be true. So here, P and Q are both true. So true implies true, true is true. What about negation? P implies negation Q. Negation P and negation Q, both of them are false. So false implies false is true. Now let's look at the second possibility. True implies false. P is true, Q is false. P is true, Q is false. True implies false, we said is false. That is the only case where we get false. True implies false, we get false. But what about negation? P implies negation Q. In this case, right now I'm in the second case, okay? So in the second case, negation P is false, negation Q is true. False implies true, right? Negation P implies negation Q. False implies true is true. Remember again, only true implies false is false. Everything else is true. So false implies true is true. Now the next case, false implies true is true. What about this one? Negation P is true, implies negation Q false. True implies false is false. And the last case, again, false implies false is true. And true implies true is also true. So again, if I want to know these are logically equivalent or no, I have to look at these columns. So are they exactly the same? The first row are the same, second row are not the same, third row are not the same, last row are the same. So they are not exactly the same. Therefore, these are not, again, not exactly the same. So what does that mean? That means P implies Q. So let me say thus. P implies Q is not equivalent with negation P implies negation Q. All right, now the last case where we have for contrapositive. So example of contrapositives. So here, again, let's consider the same example. So the contrapositive of if it's Monday, then I'll go to the mall. Go to the mall is, so P implies Q, the contrapositive, let's remind ourselves. Contrapositive of P implies Q is defined as, see here, contrapositive P implies Q is defined as negation Q implies negation P. So you have to negate both of them and also change the assumption with the conclusion. Contrapositive P implies Q is negation Q implies negation P. Therefore here, contrapositive of if it's Monday, then I'll go to mall is if I do not go to the mall. Then it cannot be a Monday. See, if I negation Q implies negation B. So if I don't go to the mall, it cannot be a Monday. See, assuming the first statement is true, unlike the previous cases, in this case, if I assume the first statement is true, then the second statement will be also true. Let's assume that if it's Monday, then I'll go to the mall. Now, if I don't go to the mall, then it cannot be a Monday, because if it was a Monday, I would go to the mall. So regardless of, in the previous cases, the truth of the second statement was depending on my schedule. Do I also have free time, let's say on Thursday as well, to go to the mall or no? But in this case, regardless of my schedule, if the first statement is true, if on Mondays I go to the mall, then the second statement will be automatically true. If I don't go to the mall, it cannot be a Monday, because if it was a Monday, I would go to the mall, according to my assumption. Okay, so the contrapositive of this is this, and note that if the first statement above is true, then the second statement will be automatically true as well. So this suggests that these two, the contrapositive of a statement and the original statement, must be logically equivalent. So this example suggests this, but let's verify this with a truth table. The easiest way to verify whether two statements are logically equivalent or no is using a truth table. So let's verify this with truth table. So truth table. You can see we have P, Q, negation P, negation Q. P implies Q. And also negation Q implies negation P. So again, this one we can have true, 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 false, false, true, or false, false. So in this case, if both are true, then in this case, both will be false. And this will be false, true, true, false, and true, true. And then if both are true here, so true implies true, will be true. Negation Q implies negation P will be false implies false, which is also true. Now in the second row, let's look at the second row. True implies false will be false. What about this one? Negation Q implies negation P. Negation Q here is true, implies negation P is false. So true implies false is also false. True implies false is also false. And then for the next case, okay, and then the next case, we have the third row, we have P implies Q will be false implies true. False implies true is true. And negation Q implies negation P. Look at the third row, negation Q is false, implies negation P is true. False implies true is also true. And the last row, false implies false is true. And true, negation Q implies negation P will be true, implies true will be also true. So now let's look at these columns. So this column here and this column here. So these are exactly the same columns. So this means that, hence we can say that P implies Q is logically equivalent with the contrapositive. Negation Q implies negation P. So we basically show that, if I want to summarize, we show that a conditional statement is logically equivalent with the contrapositive, with its contrapositive. So let's look at one more example here. Let's say if x equals 2, then x squared is equal to 4 is equivalent with its contrapositive. And what is its contrapositive? Which is, so remember again, if P, then Q. The contrapositive is if not Q, then not P. The contrapositive of P implies Q is negation. Q implies negation P. So here, if P, then Q. If x is equal to, then x squared equals 4. The contrapositive is if negation Q. So if x squared is not equal to 4, then not P. Then x is not equal to 2. So the original statement is true, right? If x is 2, then x squared is 2 squared, which is 4. The contrapositive is also true, because if x squared is not 4, then x cannot be 2. Because if x was 2, then x squared would be 4. Not, but we are assuming that x squared is not 4. So here, both statements are true. So, and that's what we expected as well, because if two statements are logically equivalent, if one of them is true, then the other one is also true. And if one of them is false, then the other one is also false. So this is always true. And this is always the case for the case of logically equivalent statements or propositions. All right, so these are the important operators that we had to cover. So another operator that we want to cover is biconditional operator. So it will be, I think, so we were covering the operators. So this was 5 implication. Now let's look at 6, which is biconditional operator. So 6, biconditional operator. So given P and Q, then P if and only if Q. So read as P if and only if Q is true if P and Q are both true, or if P and Q are both false. So the truth table looks like this. Truth table. Truth table is, if you have a table like this, P, Q, and then P if and only if Q. So if both P and Q are true, this will be true. If one of them is true, one of them is false, this will be false. And if both of them are false, this will be also true. Now, this biconditional operator is equivalent with, logically equivalent with, what type of compound proposition do you think? So if and only if. From pre-calculus, maybe you have seen that. When can we say that P if and only if Q is true? So remember when we said when we talked about conditional statements, we said that for some conditional statements, the converse is true. For some conditional statements, the converse is not true. So if the converse is true, then we call that statement if and only if. But if the original statement is true, but the converse is not true, then that statement, that conditional statement, is not if and only if. Okay, so I will give you the examples. But so the very first thing I want to say, right, like as a important property or proposition, so it's a proposition about propositions. So if P and Q are two propositions, then a P if and only if Q is logically equivalent with P implies Q and Q implies P. See, this is what I described with words, that I said that, if and only if will be true if the statement and the converse, both of them are true. So P implies Q is the original statement, Q implies P is the converse. If both of them are true, how can I make sure that two statements are both true? By putting a conjunction between them. If I put conjunction between two statements, I'm requiring both of them to be true in order for whole statement to become true. But if I put disjunction, then I'm requiring at least one of them to be true. But here I'm requiring the statement and the converse, both of them to be true. So I have to put conjunction between them. So if the statement and the converse both are true, then the statement is if and only if. So this is a claim that I'm making here and needs proof, of course. So how can I prove this? So proof. Well, we go into the methods of proof later, but for now, you should know that every statement in mathematics, every proposition, every lemma, every theorem needs a proof. So what is the easiest way to prove here? Well, it depends on you have to always, in order to make decision about the method of proof, you have to always look at the definitions. Here I have a definition for logically equivalent. Again, for definition, I provided two versions, but the easier version was using truth table. So if I draw a truth table and look at the column corresponding to P if and only if Q, and the column corresponding to the other one, P implies Q in conjunction, Q implies P. I have to look at the column corresponding to this and column corresponding to this. If they are exactly the same columns, then I can say that these two are logically equivalent. Okay, so let's do that. So we will to prove the logical equivalence. We will use the truth table. So here is Q, here is Q, here is P, here is Q, and then I have P if and only if Q. And then I have, so for the other one, in order to construct the other one, the column corresponding to this, I need to know, I need one column for P implies Q, one column for Q implies P, and then one column for conjunction of these two. So one column for P implies Q, one column for Q implies P, and one column for P, P implies Q, conjunction Q implies P. Okay, so again, I have four possibilities like always. Both of them could be true, or P true, Q false, or P false, Q true, or both of them could be false. Okay, and then so in this case, so for if and only if we say that it's true if both of them are true. So in this case will be true, or it's true if both of them is false. So in this case will be also true, and otherwise it will be false. Now let's look at P implies Q. P implies Q if both of them are true is true. Q implies P is both of them are true. Again, it will be true. And then the last column is this column, conjunction this column. How can I find the conjunction? Conjunction of two statements will be true if both of them are true. If one of them true, one of them is false, then the conjunction will be false. And of course, if both of them false, again, conjunction will be false. But here, both statements are true, so conjunction will be also true. Okay, so that's for the first row. Now let's look at the second row. True implies false. Look, I want to fill this column first. So P is true in the second row. P is true, Q is false. True implies false is false. What about Q implies P? Q implies P, again, I'm still in the second row. Q implies P means false implies true. False implies true, do you remember, is true. And finally, the last column is this column, conjunction this column. False conjunction with true will be, false implies true, false conjunction true will be false. So similarly, let's fill this column. False implies true is true, and then this one will be false, and this will be false as well. And this one will be true, this one will be true. True implies true conjunction true is true. Now I have to look at the columns, because remember, what is my goal here? To show the equivalence of P if and only if Q. With P implies Q, conjunction Q implies P. So I have to look at the column corresponding to P if and only if Q, and the column corresponding to P implies Q, conjunction Q implies P. So again, why these two columns, not some other two columns? Because this is what the question is asking from me. The proposition is asking me to prove the logical equivalence of, again, look at the question, this statement and this statement. So I have to look at the column corresponding to this statement and the column corresponding to this statement. Are they exactly the same in each row? Yes, in the first row, they're both true. Second row, both false. Third row, both false. Last row, both true. So these are exactly the same. So hence, we can say that P, if and only if Q is logically equivalent with P implies Q, conjunction Q implies P. Okay, let's look at an example. So I can say x squared is equal to 4 if and only if x is equal to 2 or x equals -2. Why is this true? Because the statement and the converse are both true. Because, if x squared is 4, then x is equal to 2 or x equals minus 2. And if, so also if x is equal to 2 or x is equal to minus 2, then x squared is equal to 4. This is also true. So recall by, let's say, note by proposition above, if a statement and its converse are both true, then that statement is if and only if and only if statement. So we can write it here this way: x squared equals 4 if and only if x equals 2 or x equals minus 2. Or you could also write it as x squared equals 4 if and only if x is equal to 2 or x equals minus 2. So you can write with words if and only if, or you can use a two-sided arrow, because again, two-sided arrow is a notation for if and only if. Okay. So this is the case where we use if and only if. Again, if and only if means the statement and the converse are both true. So for example, you can get a good grade in this course if and only if you study hard. This is true, right? Because again, the statement and the converse are both true, meaning that if you study hard, you get a good grade in this course. And the converse is also true. What is the converse? The converse is if you get a good grade, then you must have studied hard. So it's an if and only if statement that you get a good grade if and only if you study hard. But let's say, let's assume that if I want to take, for example, Math 120, Discrete Mathematics I in, let's say, some other university as a student, then this statement will not be if and only if for me. Because if I study hard, I get a good grade. But because I already have knowledge about this course, so if I get a good grade, I cannot conclude that I have studied hard. Even without studying hard, for in the case of me as a student, I still can get a good grade. Okay, so some statements are if and only if, some statements are not if and only if. Okay. Okay, so this topic of logical equivalences is an important topic. So we did few examples, but there are many more examples and exercises where you can show logical equivalence of two compound propositions. So next time we'll look at a few more types, but let's say as an exercise until next time. So exercise suppose that P and Q are two propositions. Show that, let's say P conjunction Q is logically equivalent with, negation of P conjunction Q is logically equivalent with negation P disjunction negation Q. So that's one part. And the second part is negation of P disjunction Q is logically equivalent with negation P conjunction negation Q. So these are called De Morgan's law. So I'm sure you have heard about De Morgan's law, at least in set theory. Complement of A intersection B is A complement union B complement, and complement of A union B is A complement intersection B complement. So it's very similar to that, but instead of complements, we have negations, and instead of union and intersection, we have disjunction and conjunction. But the idea is very similar. So as an exercise, try to prove these two statements. So as a hint again, remember, how would you show the logical equivalence of two compound propositions? It's very simple. Just use truth table. That's the easiest way to do. Again, I did many examples, right? So it has, again, 4 rows. And then for each row, you will find the column corresponding to, for example, in this case, corresponding to negation P conjunction Q, and find the column corresponding to negation P disjunction negation Q, and then compare them. If they're exactly the same, that means they're logically equivalent. Okay, so please try to do this one for this exercise for before the next lecture. And yeah, I always upload the lectures by one lecture by end of Monday, and one lecture by end of Thursday. Okay, guys. So thank you and see you soon.